The tangent line problem. One of the problems that's been solved by calculus is this tangent line problem. And the tangent line problem is the problem that asks, how can we find the slope of a line that is tangent to the graph of a function at a single point? Now, by tangent, we mean that the line will touch the curve without actually crossing it. So that's what we mean by tangency, or point of tangency. And we want to come up with the equation of that tangent line. So we start with a function f, and what we want to do is we want to find the equation of a line that's tangent to f. Well, to find an equation of a line, we can use a point on the line and the slope of the line. So we'll have this point on the line called a point of tangency. That point is where x is equal to c, and since the name of the function is f, the y value is the f of c. This means that to find a line tangent to a graph of a function f at the point c comma f of c, we need to find the slope of the tangent line. Because we already have a point, the only other thing we need is the slope. We will approximate this slope using a secant line through the point of tangency and a second point on the curve. That second point on the curve is a distance of delta x away from that first x value of c. So the second x value is c plus that distance delta x, which is the distance from c to the second point's x value. And that second point is going to create this secant line. So a secant line goes through 2 points on the curve, and it actually crosses the curve at both of those points. So this is the secant line, and what we're going to do is we're going to use this secant line to approximate the slope of the tangent line. So first I'm going to need to find the slope of this secant line. Well, the slope of the secant line I can find using the slope formula, which says that the slope of a line is the change in y, y2 minus y1, which is just rise or a change in altitude, over a horizontal change, x2 minus x1, which we already have called delta x. So the difference between the two x values, we already know that that's delta x. This is rise over run. Okay, so what we're going to do then is we're going to look at the vertical change, which is the difference between the two y values. That's going to be the f of c plus delta x minus the f of c. That's going to be the rise, the vertical change. And the horizontal change run is going to be x2, which is c plus delta x, minus x1, which is c. But c plus delta x minus c is just delta x itself. So plugging those things into the formula, y2 minus y1, which is that vertical change, this, and x2 minus x1, which is that horizontal change, which is c plus delta x minus c. The c minus c cancels out, and we get this difference quotient. The slope of a secant line can be found using this difference quotient, which is the f of c plus delta x minus the f of c, all divided by delta x. Okay, so let's see how this can help us to find the slope of a tangent line. All right, so more accurate approximations of the slope of the tangent line can be obtained by choosing a second point that is closer to the point of tangency. As you can see by the illustration there, the closer that second point gets to the first point, the more the secant line is an accurate approximation of a tangent line that wouldn't actually cross the function. You'll also notice that as the second point gets closer to the point of tangency, delta x, which represents the distance between them, gets closer to 0. This leads to the following definition. If f is defined on the open interval containing c, so you see this function f is definitely contained on an interval containing c, and if the limit m equals the limit as delta x approaches 0 of the f of c plus delta x minus the f of c all divided by delta x exists, so if that limit exists, then the line passing through c comma f of c with slope m is the tangent line to the graph of f at the point c comma f of c. So this is how we solve the tangent line problem, by creating a secant line and then letting the distance between the 2 points diminish to 0. Let's take a look at an example of this. Find the slope of the tangent line to the graph of f of x equals negative 3x squared plus 5x minus 2 at the point where x is 2 and y is negative 4. So if you plug 2 into this function, it spits out negative 4 as an output. I'll just plug all of this into my limit of my difference quotient. So the m, which is the slope of this tangent line, is the limit as delta x approaches 0 of the f of c plus delta x minus the f of c divided by delta x. In this case, c is equal to 2. What I'm going to do is I'm going to calculate all the parts of this difference quotient. First, I'm going to calculate the f of c plus delta x, which would be in this case the f of 2 plus delta x. So the f of 2 plus delta x is what I get when I plug 2 plus delta x in for all the x's here. So that's going to be negative 3 times 2 plus delta x squared plus 5 times 2 plus delta x minus 2. First, I'm going to go ahead and I'm going to FOIL 2 plus delta x squared. So that's going to be 2 times 2, which is 4. Then 2 times delta x, which is 2 delta x. Then inside would be 2 times delta x again, which is another 2 times delta x, which gives me 4 times delta x when I add those two together. And then delta x times delta x is just delta x squared. So from here to here, all I've done is I've FOILed the 2 plus delta x squared. Now I'm going to distribute the negative 3 and the 5. When I distribute the negative 3, I get negative 12 minus 12 delta x minus 3 delta x squared. When I distribute the 5, I get 5 times 2 is 10, and then 5 times delta x is 5 delta x. Combining like terms here, let me see. Negative 12 plus 10 is negative 2 minus 2 gives me negative 4. Negative 12 delta x plus 5 delta x gives me negative 7 delta x. And there's the negative 3 delta x squared right there. So this expression is the f of 2 plus delta x, or the f of c plus delta x from the formula. The other thing I need to know is the f of c, or the f of 2 in this case, because c is 2. But we already know that it's negative 4. That's going to be 2 squared is 4 times negative 3 is negative 12, plus 5 times 2 is 10. So that's negative 12 plus 10, which is negative 2 minus 2, and we get negative 4. All right, now I'm just going to plug all of this into my limited difference quotient. So there's the f of 2 plus delta x. There's the f of 2. I'm plugging those both into the numerator here. So that's the f of 2 plus delta x is right here, and the f of 2 is right here, and that's all divided by delta x, and I'm taking the limit as delta x approaches 0. So I just plug everything I know into this formula for the slope of the tangent line, and then the negative 4 and the minus negative 4, which is basically plus 4, they cancel. That's negative 4 plus 4, and I'm left with this. Direct substitution here, well, that's negative 3 times 0 minus 7 times 0 divided by 0. That's equal to 0 over 0. That's an indeterminate form. Whenever I get this indeterminate form, I know I'm either going to have to factor and cancel, I'm going to have to rationalize, or I'm going to have to simplify the complex rational expression. In this case, I notice that the numerator, both terms have a factor of delta x that I can factor out. So I factor out that delta x, and when I factor out that delta x, I can cancel the delta x in the numerator and the denominator. Once I cancel those, I'm left with this. The limit as delta x approaches 0 of negative 3 delta x minus 7. And now direct substitution, I get negative 3 times 0, which is 0, minus 7. So I find that the slope of the tangent line at the point 2, negative 4 is equal to negative 7. This is the definition of the slope of a tangent line. This definition, if we replace the c in the definition with the variable x, we get actually a definition for something called the derivative of the function f at the point x. So this, if you take a look, is pretty much the same definition, except for the fact that c, which is a constant x value, a specific x value, is replaced with the variable x. So when we do this, the expression we get is not just going to be a number, it's going to be a function of x. All right, so let's look at an example of this. Use the definition of a derivative that was on the previous slide to find the derivative of f of x equals x cubed plus 8. I'm using the same definition, except here I don't have the point of tangency. The point of tangency is going to be arbitrary, and we're just going to use the x value to represent the x value of the point of tangency. I just am going to use this definition then. This is the definition of the derivative, f prime of x. And in this case, f of x is equal to x cubed plus 8. I'm just going to plug that in. So the f of x plus delta x is x plus delta x cubed plus 8. And the f of x is this, x cubed plus 8. So plugging that in, I get that the f prime of x is the limit as delta x approaches 0 of x plus delta x cubed plus 8, which is the f of x plus delta x, minus the f of x, which is given, and that's all divided by delta x. Now I'm going to go ahead and I'm going to multiply out this x plus delta x cubed. That's x plus delta x times x plus delta x times x plus delta x. When you do all that algebra, you get x cubed plus 3x squared delta x plus 3x delta x squared plus delta x cubed and then plus 8. You can also use the binomial theorem to expand this. Now I'm going to distribute this negative 1 to both of those terms. I get negative x cubed minus 8 instead. So here I have the f of x plus delta x minus the f of x divided by delta x, that difference quotient. I'm just going to simplify that a little bit. Well, it turns out that the x cubed and the negative x cubed are going to cancel, and the plus 8 and the minus 8 are going to cancel. And when I cancel those, I'm left with this derivative, the limit as delta x approaches 0 of 3x squared delta x plus 3x delta x squared plus delta x cubed, all divided by delta x. When I do direct substitution, on top I get 0, on the bottom I get 0. So directly substituting 0 for delta x gives me the indeterminate form. Now when I get this indeterminate form, I know I'm either going to factor, rationalize, or simplify a complex rational expression. In this case, I notice that all the terms in the numerator have a factor of delta x. So I factor delta x out of all three terms in the numerator, leaving me delta x times 3x squared plus 3 delta x plus delta x squared. Then I can cancel the delta x on the top and the bottom. So I have a factor of delta x on top, a factor of delta x on the bottom. I can cancel them out, leaving me with the limit as delta x approaches 0 of 3x squared plus 3x delta x plus delta x squared. In this situation, substituting in delta x, direct substitution leaves me with just f prime of x is equal to 3x squared. This expression, 3x squared, this function is the derivative of the function f of x equals x cubed plus 8. The original function has another function, f prime of x, called its derivative, and that derivative function is defined this way. This is the definition of the derivative. We found the derivative of x cubed plus 8 to be 3x squared. Let's look at another example. So use the definition of the derivative to find the derivative of f of x equals negative 5 over x. Here's the definition of the derivative. This limit is going to give me an expression called the derivative of the function f. So I'm just going to plug everything in here. The f of x plus delta x is negative 5 over x plus delta x, and then that's minus the f of x, which is negative 5 over x, all divided by delta x. I'm taking the limit as delta x approaches 0. If I do direct substitution, I get negative 5 over x minus negative 5 over x, which is 0, divided by 0. So direct substitution gives me the indeterminate form 0 over 0. But because this is a complex rational expression, I can actually simplify it by getting a common denominator. In this case, the common denominator is going to be x times x plus delta x. All right, so the first fraction, well, that has the x plus delta x factor. It would be missing the x, so I multiply the top and bottom by x. And I get negative 5x divided by x times x plus delta x. The second fraction is actually missing the factor x plus delta x, that binomial. So I multiply the top and bottom by x plus delta x. Now that these two fractions in the numerator have the same denominators, I can actually combine them into one fraction, and that fraction is this. And now I have a fraction, which is this numerator here, divided by another fraction, which is delta x over 1. So we use the keep change flip. We keep the top fraction the same. We change it from division to multiplication, but we flip the bottom fraction over, making the bottom fraction 1 over delta x. Well, 1 over delta x multiplied by that top fraction gives me this. There's the delta x in the denominator of this top fraction now. And then I can combine like terms. I have negative 5x plus 5x. Those are going to cancel. And now I get this expression, 5x divided by x times delta x multiplied by x plus delta x. And I notice there's a common factor on the top and bottom. The common factor on top and bottom is delta x. So I cancel that delta x out, and I'm left with this expression. And now direct substitution, if I plug 0 in here for delta x, I'm just going to get 5 over x times x, which is 5 over x squared. The function negative 5 over x, the derivative of this function is the function 5 over x squared. And there we found the derivative of a second function. All right, let's revisit our original definition. So here, we want to find an equation of a line. So we want to find an equation of a tangent line, but I'm going to kind of define the geometry a little bit different here. Still going to have the function f, still going to have the point of tangency c comma f of c, but instead of defining the distance delta x between this x value and the next x value, I'm just going to call the next x value x. I'm not defining the distance between them, I'm just calling it x, which means that the y value for that point is x comma f of x. And there I have a secant line that goes to the point c f of c, x f of x. And I'm going to once again want to find the slope of that secant line. So the slope of that secant line is going to be y2 minus y1, which is the f of x minus the f of c. And that's going to be divided by x2 minus x1, which in this case is x minus c. So I get this expression, a different difference quotient. So this difference quotient is the f of x minus the f of c divided by x minus c. And just like before, we can do the same thing. We can have more accurate approximation by letting x get closer and closer to c, basically by letting the second point get closer and closer to the point of tangency. Note that as the second point gets closer to the point of tangency, x gets closer to c. This leads to the following alternate definition for the slope of a tangent line. If f is defined on an open interval containing c, and if the limit m equals the limit as x approaches c now of the f of x minus the f of c divided by x minus c, if that limit exists, then the line passing through c comma f of c with slope m is the tangent line to the graph of f at the point c comma f of c. So here we go. Let's look at an example. It says, find the slope of the tangent line to the graph of f of x equals the square root of x at the point 9, 3. Once again, we're just using this definition of the slope of a tangent line. And plugging in the function f of x equals the square root of x, we get that this is the limit as x approaches 9, because 9 is the value of c from this ordered pair. So it's the limit as x approaches 9 of the square root of x minus the square root of 9 over x minus 9. We know that the square root of 9 is just the number 3. So it's the limit as x approaches 9 of the square root of x minus 3 over x minus 9. Direct substitution in this case gives me the square root of 9, which is 3, minus 3 on top, so that's 0, over 9 minus 9, which is also 0. So I get the indeterminate form again. In this situation, though, because I have that square root in the numerator, I'm going to go about this by rationalizing the numerator. To rationalize the numerator, I multiply both the top and the bottom of this fraction by the conjugate of the square root of x minus 3, which is the square root of x plus 3. So I multiply the top and bottom by the square root of x plus 3, which leads to this expression. And now I'm just going to multiply out the top. I'm not going to multiply out the bottom, only the top. The square root of x times the square root of x is the square root of x squared, or x. The square root of x times 3 is 3 square roots of x. The square root of x times negative 3 is negative 3 square roots of x. Those cancel. And then negative 3 times positive 3 is negative 9. So on the top, I get x minus 9. And on the bottom, I'm not multiplying that out at all. On the bottom, I'm just going to keep it the same. So now I can cancel out that x minus 9 factor, canceling out the x minus 9, and I'm left with 1 over the square root of x plus 3. Once I get this 1 over the square root of x plus 3, now I can do direct substitution. When I do the direct substitution, I get 1 over the square root of 9, which is 3, plus 3. That's 1 over 3 plus 3, which is 1 over 6. And this would be the slope of the secant line.